Welcome to Visual Algebra Lecture 4.10, Internal Products. Previously, we've seen how to take two unrelated groups and put them together to make a direct or semidirect product. This is called an external product, and the binary operation is defined on the Cartesian product. In contrast, sometimes a group G is isomorphic to a direct or semidirect product of two of its subgroups. This is called an internal product. We'll state and prove conditions for this to happen, and then we'll learn how to identify it by inspection, both in a subgroup lattice and in a Cayley graph. We'll finish with the concept of a central product, which results by modifying these conditions. Some of the techniques learned in this lecture will be used throughout the rest of the course, especially in the later chapters on extensions and even Galois theory, so you're not going to want to miss it. Let's get started. We've seen how to define the direct product of two arbitrary groups, A and B. This is called an external or outer direct product. Sometimes a group is secretly the direct product of two of its subgroups. That is, G is equal to NH, but also isomorphic to N cross H. This is called an internal or inner direct product. We've seen how to define an external semidirect product of two arbitrary groups A and B in the previous lecture. In this lecture, we'll learn how to identify when G is an internal semidirect product of two of its subgroups. That is, when a group G, which is the product of N and H, is also isomorphic to the semidirect product of N and H. When this happens, the labeling map, that's what I call the homomorphism from H into the automorphism group of N, sends the element little h to an inner automorphism, that is just conjugation by H. That's why some sources call this the inner semidirect product instead of internal. Whatever you call it, the inner direct and semidirect products can be identified by inspection of the subgroup lattice. And that's what we'll see in this lecture, and that's what we will use going forward in a number of chapters throughout this course. We'll also learn about central products, both external and internal, though I will only define the internal ones by modifying the conditions needed for an internal semidirect product. Let's get started with an example right away. Previously, we've looked at outer products, that is, taking two unrelated groups and constructing a direct or semidirect product. Right now, we'll explore when a group G, which is the product of its subgroups N and H, is isomorphic to a direct or semidirect product. Once again, these are called internal or inner products, and here are two examples, one direct and one semidirect. The first one, G is equal to C6. And N is generated by R squared. This is isomorphic to C3. And H is isomorphic to C2, generated by R cubed. C6 is the direct product of these two subgroups. And here's how we would express the labeling map if we wanted to do our semidirect product construction. Over here, we have D3. And let's take N generated by R, C3, and H generated by F. So it's the same two subgroups as we have over here. But now the so-called labeling map is different because the presentation is different. And D3 is a semidirect product of C3 with C2. Questions that you should be asking yourself. How can we characterize when this happens? Like, when is a group isomorphic to the direct product of two of its subgroups, or a semidirect product of two of its subgroups? And when the latter happens, what is the actual labeling map? How can we characterize it? Starting with direct products, when G is isomorphic to a direct product of two of its subgroups, then we have an isomorphism from the direct product N cross H to the product NH that sends an ordered pair of elements little n little h to the product little n times little h. Since N cross the identity and the identity cross H are normal subgroups, then these, through this isomorphism, get mapped to N and H, which have to be normal in the product NH. Recall that earlier we showed that the order of the product NH is the size of n times the size of h divided by the size of the intersection of n and h. And so it follows, at least if G is finite, we'll handle the infinite case later. Actually, we can handle these together, but that if we have such an isomorphism, then these subgroups have to intersect trivially, because the size of this is this and the size of that one is that. Here is a theorem for when G is isomorphic to a direct product of two of its subgroups, n and h. So this happens if and only if the following conditions hold. N and h have to be normal, they have to intersect trivially, and then they have to generate G. Remember, if n and h are normal, then nh will be a subgroup, and it's the smallest subgroup contained in both n and h. This has a very nice interpretation in terms of subgroup lattices. Subgroups for which conditions 2 and 3 hold are called lattice complements. So together, these three conditions can be described as G having a pair of normal subgroups that are lattice complements. In terms of the subgroup lattice, this is usually fairly easy to spot by inspection. So if we have a pair of subgroups n and h, being lattice complements means that they intersect trivially and they generate the entire group. And if they're both normal, then G is equal to n times h. We only need normality of one of them. Actually, we don't even need that much. And it's isomorphic to the direct product of n and h. So being able to spot such a pair of subgroups will be a very useful tool going forward. Now let's look at semidirect products. When G is isomorphic to a semidirect product of n and h, we have an isomorphism from the semidirect product to the product nh. It's the same one as before. It sends an ordered pair of elements, little n, little h, to the product little n times little h. This time, only n cross the identity needs to be normal in the semidirect product. And so this normal subgroup passes through the isomorphism, and it means that n is normal in the product. In other words, n is normal in G. As before, from the equality that the order of nh is the order of n times the order of h over the order of the intersection, we conclude that, at least for finite groups, if nh is a semidirect product of nh, then n and h have to intersect trivially. Here's the analogous theorem for semidirect products. It says that G is isomorphic to a semidirect product of n and h if and only if the following conditions hold. First of all, just n has to be normal in G, not h. But the next two conditions are the same. N and h have to intersect trivially, and they have to generate G. So in other words, they still have to be lattice complements. When we have a semidirect product, we have a labeling map, theta, from H to the automorphism group of N. And this one, it's natural to ask, what is that labeling map? And it sends an element, little h, to an inner automorphism. That is an automorphism that's just conjugation by H. Now, a quick reminder, I've been calling the inner automorphism that sends an element to H, N, H inverse, I've been calling that phi H inverse, and analogously, H inverse N H I've been calling phi H. In other words, whichever element is last is what I've been using for my naming convention. And remember why that was. That's because using this convention, phi of x times phi of y, if we read from left to right, equals phi of xy. So because we're reading from left to right, it's more natural to use this convention, which one downside is that it would be nice if we could just say that this labeling map sends H to the inner automorphism phi H, And that's what we would use if we read right to left. But unfortunately, this has to be H inverse for this all to work out. But that's really no big deal. Let's do several examples to get some intuition before we actually prove this theorem and the previous one. Here is the semidihedral group SD₈ and the generalized quaternion group Q16. And I encourage you to pause the video and find as many lattice complements in these lattices as you can, for which at least one of them is normal. Okay, I'm about to show you the answer. The group SD₈ decomposes as a semidirect product in two ways. So here is the non-normal subgroup H, and we can take the normal subgroup N1 to be this. So this is C8 and this is C2. Or we can take a normal subgroup N2, which is this one here. And see this little kite-shaped lattice? You should recognize that as the quaternion group. So in other words, SD₈ is a semidirect product of C8 with C2, but also of Q8 with C2. What about the quaternion group over here? Well, we can see that there are no lattice complements other than the trivial one of G and the trivial group, because any two of these subgroups will intersect in this subgroup of order 2. Remember, this is the one that you can think of as being generated by -1. It's the center. Let's return to this semidihedral example and interpret it in terms of subgroup lattices. So this has 3 index 2 subgroups. The first one is isomorphic to D₈, and you should be able to recognize this subgroup lattice. The second one is isomorphic to C8. You should definitely recognize that subgroup lattice. And then the last one has this kite-shaped subgroup lattice, so you should recognize that one as Q8. Here are the corresponding subgroups in the Cayley graph. So D₈ is generated by R squared, a 90-degree rotation, and S. C8 are just the rotations, or I should say the powers of R, abstractly the rotations, and Q8 consists of these highlighted elements here. So notice that SD₈ does not break up as a semidirect product of D₈ with anything else, because there is no order 2 subgroup that is that intersects trivially with it. All of these things are contained in it. There's nothing over here. And in terms of the Cayley graph, none of these nodes that are not in the subgroup have order 2. So what we would need is a subgroup of order 2 that intersects trivially with it. But none of these 8 nodes have order 2. Here with C8, we have such an element of order 2. So here's the subgroup, and let's take S. This is a subgroup of order 2 right here, and it intersects trivially with the subgroup here. You can see that in the subgroup lattice. S and subgroup generated by S and R intersect trivially. Finally, Q8 is the same thing. The subgroup generated by S, these two elements, intersects trivially with the subgroup consisting of these 8 elements in yellow. And indeed, this subgroup, let's call it H, as before, intersects trivially with Q8. We saw the generalized quaternion group Q16 earlier, and here is Q32. Recall that a generalized quaternion group is just a dicyclic group whose order is a power of 2, and these have properties that other dicyclic groups do not. And the important one, to me anyways, is that any 2 non-trivial subgroups will intersect in at least this order 2, or the unique order 2 subgroup, which you can think of it as generated by -1. So if you take any of these order 4 elements in the inner ring, the square of it is R8. So that's why all of these order 4 cyclic groups contain the subgroup generated by R8. And then because n is a power of 2, if you take any element here and you repeatedly multiply it by itself, you will get to r to the 8 before you get to r to the 16th, which is the identity. So all of these other cyclic subgroups, I guess there's just these three, will contain this subgroup as well. So as a result, Q32 does not break up as a semidirect product of any two of its non-trivial subgroups either. I mean, it is trivially the semidirect product or direct product of this with the trivial group, but that's not interesting. And this is a property for all generalized quaternion groups. They all have this subgroup structure. They look like a dihedral group on a stick. And on an earlier lecture, I think in chapter 3, I showed the what I call not reduced subgroup lattices, but the subgroup diagrams of the generalized quaternion groups side by side from Q4, which is that dihedral group, to Q8 to Q16, all the way up to Q32, and they had a uniform structure. And from that, you can see right away that there's no way that any of those can break up as a semidirect product of two of its proper subgroups. Now that we have some intuition about internal direct and semidirect products, let's prove the theorems that I stated in the beginning of this lecture. First, we need a lemma. If H and N are subgroups of G that are lattice complements, then they are normal if and only if elements in them pairwise commute. So if little h times little n equals little n times little h for all elements. Let's prove this. Since we have an if and only if statement, we have to prove both directions. So I will start with the forward direction. This condition here, on the right-hand side, we can write as NH N inverse H inverse being the identity, and that's just the commutator of N and H. So for the forward direction, since H and N are normal in G, let's write the commutator N comma H. I'm going to write it I'll write it twice. NH N inverse H inverse, let me write that twice, NH N inverse H inverse, you'll see why in a moment. So for the first one, I'm going to highlight these last three elements, and we're taking something in N and conjugating it by something in H, and by normality of N, that means that this thing here is in N. Similarly, if we look at this last one, and look at the first three elements, well, we take something in H and conjugate it by something in N, that will remain in H. So now, this commutator is N times something in N, so it lies in N, but it's also something in H times H inverse, so it lies in H. In other words, this lies in N intersect H, which, because these are lattice complements by assumption, is just the trivial subgroup. So in other words, we took an arbitrary commutator and we showed that it was the identity. And that proves the forward direction. Let's now prove the backwards direction. So suppose that this condition holds. So let's suppose that Hn equals Nh for all n in N and H in H. And we want to show that N and H are normal. So let's take an element, or let's take G, which is equal to NH in big G, because these being lattice complements, that means that G equals NH. And let's show that every left coset is a right coset. So GH is NH big H, which by our boring but useful coset lemma, the little h gets absorbed, so this is NH. So this left coset is NH, and it suffices to show that it is a right coset. So NH, by definition, is the set of all elements little n times little h, where little h is in big H. And by assumption, because these elements commute, we can write this as Hn for H in H And this is precisely Hn. And that's exactly what this is. So this left coset is equal to a right coset. And if you don't, we don't need to put the h back in here, but we certainly can. We can write this as big H, little h, n. Since h and n commute, we can write this as big H times n, or big H times nh, which is big H times g. And therefore, H is normal. And similarly, or by symmetry, n is normal. So I just picked one of these two, doesn't really matter which one. Or by symmetry, n is normal as well. And that does that, and that completes the proof. Let's prove what I stated in the beginning of this lecture. That is, if we have two subgroups n and h of G, then G is isomorphic to a direct product of them if and only if the following three conditions hold. Both subgroups have to be normal, and they're lattice complements. So they intersect trivially, and they generate the entire group. I'll prove the backwards direction first. That's really the only one we have to do. We'll talk our way through the forward direction afterwards. So let's start by defining a map. I'm going to call it I from n cross h to nh. And we're going to prove that this is an isomorphism. And the map is defined exactly how you probably think it is, which is going to take an ordered pair of little n comma little h and send it to the product little n times little h. So let's start out by proving that this is a homomorphism. And by the lemma that we just proved, elements in n and h pairwise commute. So nh equals hn for all elements n and h in their respective subgroups. So n is an n and h is an h. So now let's do I of n1 comma h1 times n2 comma h2. We just kind of follow our nose here. This is I of n1 n2 comma h1 h2. And by definition, this is n1 n2 h1 h2. And now this is where we use the fact that elements in n and h pairwise commute. So this is n1 h1 n2 h2. And now we look at what we have here. You can see that this is just I of n1 comma n h1 times I of n2 comma h2. And therefore, this map is a homomorphism. So now let's show that it's bijective. So we'll do onto. This is straightforward. If we have an element in the codomain, nh, then I can tell you what it comes from. So let's just write that down, but we don't really have to. nh in big N times big H has preimage n comma h in big N cross big H. And that's that. Now let's show that it's one-to-one. So let's suppose that we have two inputs that map to the same output. So suppose that I of n1 comma h1 equals I of n2 comma h2. And that is equivalent to say that n1 h1 equals n2 h2. Well, if that happens, that's the same thing as saying we can move things over and write n2 inverse n1 equals h2 H1 inverse. And so this now is in N, and this now is in H. And since these are last complements, that means that this is in N intersect H, which is the identity. And so that means that, well, if N2 inverse N1 is the identity, that means N1 equals N2. So let me move over here. That means that N1 equals N2 and H1 equals H2. And that's what it means for these inputs to be the same. I almost don't need to write this down, but it means that N1 comma H1 equals N2 comma H2. And that's what it means for the map to be injective. If two things get mapped to the same place, they were the same to begin with, and that's the end of the proof. So that proves one direction. If these three conditions hold, then G is a direct product of these two subgroups. And conversely, let me just talk our way through it. If we have a direct product and an H, then we know that N cross the identity. So let me just make a few notes here. So N cross the identity and the identity cross H are both normal. And those things will get mapped to N and H respectively, be this isomorphism. And since this is an isomorphism, these will be normal as well. So right away we've got this one. And we know that in the cross product, the direct product, these things intersect trivially and they generate the whole thing. And so as we push them through the isomorphism here, the images will as well. So once we establish the isomorphism, we basically get both directions of this. Let's now prove the analogous statement for semidirect products. So this time we have lattice complements when only one of them is normal. In particular, if N and H are subgroups of G, then G is a semidirect product of N and H if and only if the following conditions hold. One of them has to be normal. Let's, without loss of generality, say N, because N for normal. And then N and H are lattice complements. So they intersect trivially and they generate G. So G is N times H. In this case, if we have a semidirect product, we have a labeling map. That is a homomorphism from the non-normal group to the automorphism group of the normal group. And I claim that this is the one that sends an element H to the inner automorphism where we conjugate by H. So N gets sent to H, N, H inverse, and unfortunately, because we read left to right, we have to call this inner automorphism phi H inverse instead of phi. Let's prove this. So you'll see that it'll be very analogous to the last one. So as before, we will define the map I from this time the semidirect product to NH. And remember, this can be defined on the set of ordered pairs of N comma H. So we're not worried about at this point, we're not worried about the binary operation. So I, as before, is going to send N comma H to N times H. So let's first prove this is a homomorphism. We got to be careful because what does it mean to be a homomorphism? Well, we have to show that we have a different binary operation in both of these things. So in the input, we have, in the domain, we have I times N1 comma H1 star N2 comma H2, and this is that that sort of twisted product where we have to stick an automorphism in here first, and if you don't remember what that is, I'll remind you very shortly. But we have to show that this is equal to I of N1 comma H1 times I of N2 comma H2. And this is just the standard multiplication in NH, and we actually know what this is. So this is N1 H1 times N2 H2. So we really have to figure out, what this thing is and show that this is equal to that. And I should say that, as before, I didn't write this down, but I'm going to prove the backwards direction, and then we'll just talk our way through the forward direction. The meat here is really showing that these two things, there's an isomorphism between these two things. Okay, so let's compute this. I of N1 comma H1 star N2 comma H2. Remember how this is defined? Well, this is I times N1 times H1 N2 H1 inverse. Again, I am assuming, so we're going the backward direction, so I'm assuming that this is the automorphism. So we apply this automorphism to the N2. And then the second coordinate, nothing changes. So for the second coordinate, we have H1, H2. And I should probably do that. So now we just have the map I of an ordered pair, and we know how to define that. So we just multiply these things together. So this is N1, H1, N2, H1 inverse, and look what happens. Now we have H1, H2, and I think you see the idea here that we cancel those things. So what's left? Now we have N1, H1, N2, H2, and look, that's exactly equal to what we needed it to be equal to. And so therefore, this map is a homomorphism. And what about the bijection? So we only need this operation to show this is a homomorphism. We know this is a bijection because we showed it in the previous slide. This is the same map. We're really going from ordered pairs to elements, to products. The fact that it's a direct product or semi-direct product doesn't matter. So let me just say that for bijection, this is analogous to the direct product case. And that's the backwards direction, but let's talk our way through the forward direction. So we just showed that if we have this, now we have or if we have these conditions, then G is isomorphic to a semi-direct product. But we also know that if we have, G is isomorphic to a semi-direct product, we can define this map like this. We can prove that, and we're going to, so G is isomorphic to semi-direct product, I should say, with this inner automorphism. Then we can push it through. We can say, well, N is normal in here, so therefore, N, so there's the subgroup N. I'm going to actually write it as the N cross the identity. That's going to get mapped to N. And so if this is normal, that's going to be normal. So that gets, because this is an isomorphism, this normal subgroup gets mapped to normal subgroup here. And we also know that N cross the identity and the identity cross H, these things both intersect trivially and generate the whole thing. And so these things come through automatically as well. So I should have maybe clarified that this is a semi-direct product, theta, where this is the inner automorphism if and only if this holds. Because we really do need this definition in order to show these things. One of the really powerful things of the theory that we just learned is it allows us to, in many cases, take a group, look at a subgroup lattice, and in a matter of seconds, tell how it breaks up as a direct or semi-direct product of its proper subgroups. And this is because we can usually spot by inspection pretty easily pairs of lattice complements, and we often know whether one or more of them are normal. Let's do an example. I really like this one. This is the dihedral group D6. And I want to ask, in how many ways does it decompose as a direct or semi-direct product of its subgroups? And I want to ignore the trivial one of D6 cross the trivial group. So I encourage you to pause this lecture and take a few moments to think about this. And also, I'm looking for a truly distinct way. So I don't mean the subgroup generated by R and RF or R cubed F or R fifth F. Those, in both these cases, this is the semi-direct product of C6 with C2. Okay, so pause the lecture, try to figure it out, and come back and see if you get all of them, or if you miss one or two. Okay, so welcome back. There's actually 4 of them that are distinct. Do you see them? So there's C6 and C2. There is, you can use one of these C2s or one of these C2s. It doesn't matter. There is D3. See how that's D3? And one of these C2s. So this is a semi-direct product of D3 and C2. Well, there's also this is C3 and V4. These things are lattice complements. And then there's actually a direct product in here as well. So there's D3. You can take the C2 that's in the center. That's not contained in either of these. And now both of these are normal, so you get a direct product. Let's look at this in terms of the Cayley graph. So C6 semi-direct product C2. Let's just use this F. So C6 is here. And then there's an element of order 2 that intersects trivially with it. So there's your lattice complements. One of these is normal. What else is there? I think the others are a little bit harder to see. If you have D3, let me highlight one of these. So that's, let's do the one that's R squared and F. So it's these things here. So if you have these, and then you have so here's your normal subgroup, next 2, and RF right there. There's an element of order 2, and this subgroup right here is going to intersect trivially with these, with the D3 here. And then what else is there? There's, if you take this other one, if you take this subgroup, then that also acts trivially, but this one is normal. So there's your direct product. And then I think it's a little hard to see this C3 and V4, but let's see if we can do it. So I'll use a different color. So here's a V4. I haven't tried this before. We'll see if it works. And then there's your C3 right here. Yeah, so these things do intersect trivially because, again, here's 4 and here's 3, and then they generate the whole thing. I think it's not quite as easy to see as like with the C6 where you see this thing right here and you see an element of order 2. That's not in it. Here's a picture of that in terms of the subgroup lattices. Here are those 4 decompositions. Again, D6 is isomorphic to a semi-direct product of C6 with C2, with D3 with C2, with C3 with V4, and then as a direct product with D3 with C2. So we'll come back to these examples, especially in Chapter 6 when we look at group extensions. And we will learn about how to represent these with short exact sequences. Here are the decompositions of D6 into direct and semi-direct products in terms of Cayley graphs. So these 4 are in the same relative position as the one in the previous slide. Notice this is C6 with C2. This is D3 with C2. See how these things are rewired a little bit. These red arrows are reversed. Here the colors are reversed. C3 semidirect product V4. Remember the first one, this is, remember our convention of A semidirect product B. So A is the one that gets rewired. B are the balloons. So here we have these V4 balloons, and we have rewired copies of C3 in here. Be really careful with how you label these nodes. I had several mistakes. They were not how I thought they would be when I first made this image. And then finally, we have a direct product of D3 and C2. So these are not rewired because it's a direct product. You also have to be careful with how you label these things. I did not expect these to be labeled the way that they were. I want to finish this lecture by talking about central products, and in particular, I want to compare them to direct products. So the following three conditions characterize when G is a direct product of two of its subgroups, N and H. N and H have to be normal, and then N and H are lattice complements, which means that they generate G. Because N and H are normal, we can write this as just NH, and then they intersect trivially. One of the key ideas in this lecture is that if we weaken this first condition to only N being normal, then G is not the direct product of its subgroups, but a semidirect product. But for central products, I want to instead keep these first two conditions, but I want to weaken the third. So now, instead of H and N intersecting trivially, I want to just require that they intersect in a subgroup contained in the center. This is called an internal central product of N and H, and it's denoted with a little circle, N circ H. I'm not really sure how to say it. I don't really say it out loud all that much. We can also define an external central product of two arbitrary groups A and B, where we kind of glue them along a subgroup at the center, but we won't do that here. I might mention a little bit more about this near the end of chapter 7, which is on universal properties, when we get to push-outs and pullbacks of groups, or actually objects in general categories. I want to finish with a really good example for both semidirect products and central products. This is the diquaternion group DQ8 and DQ16. If you're not familiar with these, I encourage you to watch my lecture from chapter 2, where I introduce these. And again, this name is mine. It's not something that you will see that much in the literature, or at least not when I'm recording this. I'm hoping that the name will catch on in a few years. We'll see. So first of all, how many semidirect products can you find of the form H with some subgroup C2? So we're looking for order 8 subgroups and some element of order 2 that intersects it trivially. Okay, I'll let you pause the video and try to find them yourself, and then come back. Okay, welcome back, if you did that at all. So one thing to look at is along this outer edge. You recognize that? That's the subgroup D4, and then there's this element here of order 2 that subgroup intersects D4 trivially. So this is a semidirect product of D4 with C2. What else is there? Well, you may remember that that this group has an index 2 quaternion subgroup. And that's kind of how we defined this group originally. We said, what if we take the quaternion group and we add in a reflection? So if we take these nodes right here, we get the quaternion group. And then here is that reflection from a dihedral group. And I say reflection because if you think of these things as matrices, this is the reflection matrix, and this is I, and one of these is, I think this one is J. One of them is J. So this is Q8, semidirect product C2. So we have Q8, semidirect product C2. And then I claim that there's one more. When I say that there's one more, there are other copies of C4 and Q8 in here, but there's a different group altogether. And that's well, do you see it? It's these 4 nodes and these 4 nodes. Oh, this is a claim in a abelian group because red, blue, green is, so it's generated by, let's see, let me just, this time I will circle these to distinguish them. So I claim this is an abelian group because it's generated by by blue, red, and green. And notice that blue, red, green equals green, blue, red. So this is an abelian group. It has an element of order 4. It does not have one of order 8. So it is C4 cross C2. So C4 cross C2. And there is a copy of C2 here that intersects it trivially. So just in a matter of seconds, we can, with a little bit of practice, spot 3 different semi-direct products of DQ8 purely by inspection. This is something that you cannot do. I don't care if you're an algebraist or if you have a fields fundamentalist, you're not going to be able to do this in a matter of seconds with just the group presentation. The Cayley graph, remember, is a visualization of the group presentation. It's nothing more, nothing less. Well, it's a little bit more because it says how many elements there actually are in the group. But it's just a visualization of that. And a lot of people, are skeptical when they see this visual pedagogy. They say, oh, this is an easy version of group theory. Trust me, it's not. Or it's an alternative for people who are visual learners, as if that's a weak thing. But really, it's a vehicle that allows me to do so much more. And you're seeing this here. You cannot make these observations just from a presentation. So it allows us to be able to say more and observe more about groups. And so it's not actually less than, if anything, it's actually certainly more than. I think it's actually harder than just standard group theory in some sense because we can actually go more and say more. So I encourage you to do the same thing over here. You can, there's a dihedral group of index 2 along the outside. There's a generalized quaternion group as before. So you take every other element here, and then you take every other element in the inside. That's Q16. And then also if you take all of the, let's pick a color. And so if you take all of these elements here in the every other axis, you will get, I think, an abelian group, which is C8 cross C4. And the pattern continues as you would expect. Okay, what about central products? Do you see any? This is harder to do in the Cayley graphs, or at least for me anyways. Let me show you the subgroup lattice. Here is the subgroup lattice of DQ8. And remember, these can be represented as 2 by 2 matrices, and the center of ZQ8 is generated by the scalar multiples of, or it consists of the scalar multiples of the identity matrix. So this is just the set of plus or minus the identity matrix and plus or minus I, that is the square root of -1, times the identity matrix. And that is the cyclic subgroup right here. Of these 4 cyclic subgroups of order 4, it's the one that is contained in 3 abelian groups of index 2, whereas all of the other ones are contained in a quaternion and a dihedral and an abelian group. So this is the center, and if you take this to be n and say k to be d4, notice that these things intersect in this central subgroup C2. They're both normal. This is index 2, this is the center, and they generate the whole thing. So DQ8 is a central product of C4 with D4. And it's also a central product of C4 with Q8 because similarly, these 2 groups intersect in, not trivially, but in this central subgroup of order 2, and these 2 things are normal and they generate G. So the diquaternion group DQ8 is a central product both of C4 with D4 and C4 with Q8, and you can check that this generalizes in a predictable way, or at least something that's not unpredictable, I would say. DQ16, whose Cayley graph you saw in the previous slide, is a central product of C4 with D8 and also with C4 with Q8. D16. Okay, so I encourage you to check that out. And if you go on group names, it's not an LMFDB, but if you go on group names, looking for these groups, this is how they are labeled within group names. Whereas in LMFDB, I think they are listed as this is listed as one of the multiple semidirect products of, I don't know, D8 with C2, and this one D16 with C2. Okay, that's a good place to stop. And that really brings us to the end of chapter 4, maps between groups. And next up is group actions, which is an incredibly important topic. But I say next up, I think I'm going to record at least one more lecture in this section. There's one that I'm thinking about, which is involves applications of homomorphisms. I mean, we think of algebra comes up all over the place in topology and geometry and number theory. But as you're learning group theory, you don't really see those or know about those. And it's easy to see, how does this stuff come up? Why am I learning this? And it actually comes up in calculus, in linear algebra, in differential equations, in trigonometry and exponentials and logarithms. That is the concept of a homomorphism. And I want to show you that. So I'm going to record a lecture that's not going to be very visual in nature, but it will show you how homomorphisms can be used to derive a lot of the formulas that we either learn and don't understand or take for granted, things like log laws and trig identities, or things like solutions to differential equations or solutions to indefinite integrals and things like that. So this is not something, things after this lecture, if I record this one and who knows, maybe at some point another one, they are not going to be required knowledge. They're optional, but they will be fun. So I encourage you to check those out and definitely stick around for group actions. One of the things that I will be doing that is typically not done in other books, besides doing everything visually, is talking about G-sets and emphasizing that. A G-set is like a generalization of a group. It is a set with an algebraic structure that in some sense generalizes a Cayley graph, and it's a really important concept to understand as you learn about group actions. And many, if not most books, don't even mention it. And I've even talked to a few professional algebraists who have looked at me and said, what's a G-set? And when I tell them, they say, oh yeah, I knew that, but I don't ever define it that way or think of them that way. And I think that's a mistake. So definitely check out chapter 5. In my opinion, even though we've been having fun up to now, chapter 5 is where things really start to get fun. So don't go anywhere.